formula for the in the real cyberwithin theory, and this is joint work with Jim Miyazawa and John Park. So let me start with reviewing what was real cyberwithin theory. So there are several variants of the real cyberwithin theory, but let me focus on the real cyberwithin theory, which uses some homotopical, homotopy theoretic description. Although there are many other authors who developed real cyberwithin theory, Tian-Wan or Nakamura or Jakairi and Barguier. So this is in the joint work with Kona and Miyazawa, 21, 23. So, and it is kind of a TQFT for given knot inside S3. You can get some output data. So this is so the Z over Hose equivariant stable homotopy type of pointed finite Z4 equivariant CW complex with some formal desuspensions. So this is corresponding, this is what we call the real Floer homotopy type. It's not like a module, it's really a space, and with some like stable or equivariant or with some formal desuspension. But if you don't know much about the Floer homotopy type, you can regard this as just a Z/4 equivariant space. And if you have a surface cobordism, so this properly embedded surface inside the Floer manifold, which is the interval times S3 plus X. So here X is closed oriented Floer manifold whose first homology is 0. And when you regard the homology class of this surface sorry, let me say this is a surface cobordism from K to K prime. And when you regard the surface class inside the relative homology, I want to assume this is this divided by 2 is still integer class inside this homology group. And also I want to assume the Poincare dual of the second Stevie-Hoekner class of X is equal to this class divided by 2. So if I write some picture, then it's like the X and some K and K prime. And I have some kind of surface cobordism. So this is, and in this talk, let me assume this is oriented. Okay. So this is input data. And then the output data we will have is kind of map corresponding to this surface cobordism, so which is a map from a real Floer homotopy type of K, which which some sphere to the to the Floer homotopy type of K prime with some suspension again. And this map will be 0/4 equivariant map. And the species I'm using here is the representation of 0/4. So let me write this group 0/4 as the group generated by J inside pin 2, or maybe cotonium. And I'm just sending J to I for the representation C, and for the other representation, I should write this as R tutor. J is going to be -1. So this is kind of corresponding cobordism map inside in this real Seiberg-Witten theory, and this is called real Bauer-Fulton invariant. Okay. Yeah, this is a review of real Seiberg-Witten theory. The input data is not all surfaces, properly inhibited surfaces like this. And then you can get the corresponding Floer homotopy type, just a space, and the corresponding some continuous map, a 0/4 equivariant continuous map. Sorry, and I forgot to say, this notion, sigma 2 S is just double branch cover. Cover along S. And this divisibility condition implies we can take the double branch cover. Okay, is there any question about this? And let me say 3 remarks. The first remark, so if you take a smoothly embedded 2-sphere, which is 2-knot inside S4, and if you puncture twice, you can get cobordism from unknot to unknot. So this is a cobordism. And then I can apply Bauer-Fulton invariant, which is a map from the Floer homotopy type of the unknot to the itself. But yeah, we can say this is just S0, and this is also S0, stably. That means, yeah, we can change this as any integer. And there is some 0/4 action on this guy. But we can forget it. Just forget it. Then I can get the stable homotopy class between a map between spheres. I can take a mapping degree. This is same. And absolute value. And this is nothing but the 2-knot invariant Miyazawa defined. This is Miyazawa's invariant. And he extended it to non-orientable case. And he detected exotic P2 knot. So this TQFT includes really interesting information, new information. And second remark I want to point out is, so if you take the 0/2 subgroup inside 0/4, just plus -1, and then if I can think of equivariant cohomology, 0/2 equivariant Borel Tate homology. And it is actually, yeah, conjectured to be isomorphic to leads real monopole Floer homology. Defined for any link. Which is written by HMR. And he provided some spectral sequence from reduced covalent Floer homology of K mirror to some version of monopole Floer homology. So this shows the kind of similarity of this real TQFT with the known Floer homology theoretical invariants. And recently, again, this is conjecture, but Manuesco and Guth gave a real Higad Floer homology, which is written by HFR. Okay. So if you forget the z over 4z action and reduce to z over 2z, then it is related to kind of other invariant. Okay. And the importance of z over 4z action is actually we can prove some kind of 10 over 8 inequality. So instead of applying the singular cohomology, we can also apply generalized cohomology, and in particular, z over 4z equivariant K theory. Then, yeah, what we can get is so-called real 10 over 8 inequality. Which gives some strong constraints on the embedded surface inside the Four manifold. And actually, there is a kind of higher version of the real Seiberg-Witten theory, which Sun-Kyan will talk in today. And combined with its higher version, actually, we could prove any even common cable of the figure 8 knot is actually infinite order in the smooth concordance group. So this will be explained in the Sun-Kyan's talk. Okay, so this is the kind of review of real Seiberg-Witten theory. Is there any questions so far? Okay, now I'd like to say the main theorem, which is about this satellite formula for this real homotopy type. So let me take a pattern, which is a knot inside S1 times T2. And we need to assume the winding number is odd. And for any knot K inside S3, so what we can get is the real Floer homotopy type of P of the K is actually equal to real homotopy type of PU, which real homotopy type of the K. So this is the main theorem today. So this is kind of very simple satellite formula. Like if you want to write down satellite similar kind of formula in the Higgs-Floer theory, it's the formula really depends on the pattern P, not like this winding number. So it's very kind of mysterious. And so if you think about the like classical algebraic concordance class, the similar type of formula can be proven. So in this sense, like real cybergrid theory has some properties similar to like some classical invariant. And then as a corollary, because this is an equality of space, we can see several equalities for numerical invariants. So let me say several numerical invariants derived from real cybergrid theory. One is degree of k. So this is just the absolute value of Euler characteristic of, the reduced cohomology of real Floer homotopy type k. So this is called degree invariant, Miyazawa defined. And the other one, delta R, this is kind of Floer type invariant for the equivariant cohomology, but 0/2z coefficient. So I want to say briefly the definition of this one. So if you think about this 0/2z action, we can prove that this module is rank 1 over the classifying space of 0/2z. So that means this cohomology looks like a one tower with other several torsion elements. It's really similar to original Higgs flare or monoball flare or maybe instant flare. So what we can think about for this concordance invariant, like we can get is just minimal, like bottom degree of the degree of this element. So this is nothing but the real Floer invariant. So, but I didn't say anything about the degree here. There is certain absolute degree in rational absolute degree in this theory. So this is well defined, and from this our convention, this lies in the 1/60z, and we can prove this is concordance homomorphism. This is concordance invariant. And we can also define the Floer invariant, Floer type invariant for the equivariant case theory. And this is called the real kappa invariant. This is also concordance invariant, and this will be defined in a similar way, but I will not explain the detail. Anyway, this is concordance invariant, which takes value in 1/60z. So, and for example, 2-1 cable of the figure-8 knot, what we can prove is if you take a 2-1 cable of the figure-8 knot, this kappa invariant is actually non-trivial, and kappa invariant of the unknot is 0. So this is not smoothly concordant. And from this satellite formula, let me suppose the pattern like PU is equal to U up to isotopy. And again, the winding number is odd. Then what we can prove is that the degree invariants are same and the other concordance invariants are all same. These numerical invariants coincide each other. Anyway, even for kappa invariant. Sorry. Screen, I wanna, should I move? Is this fine? Oh. Oh, okay, thank you. Oh. Sorry, thank you for pointing out. Sorry, thank you. sorry. Sorry. Yeah, as a corollary, what we can prove is, for example, the following in the non-concordance group. So supposing that P of the unknown is equal to P. Actually, this can be generalized up to concordance. And the winding number is odd. Then what we can prove is any, like this satellite operation with respect to P of this 2-1 cable of the figurative knot is infinite order in the smooth concordance group. So this is one application to the knot concordance theory. And let me say kind of one remark. So if you take figurative knot, and if you apply the odd pattern satellite operation, what happens is, so sorry, odd comma 1 cable of the figurative knot. This satisfies the assumption of the theorem. So we can use the equality. So this is equal to the Floer homotopy type of the figurative knot. But for the figurative knot, real Savaguitin theory completely vanishes. So this is actually equal to S0. So that means the all concordance invariants of the odd comma 1 cable vanish, but not for even comma 1.
Sorry, I just want to clarify, by P of U equals U, you mean like forgetting that it's in a solid form.
Yes, yes. Okay, so this was the first topic. So we have some satellite formula and we have several applications. So I want to change the topic. So is there any questions so far about this satellite formula? No, then I'd like to go to the second topic, which is about the relation between this real Floer homotopy type and the surgery on the knot. So of course, there are so many kind of surgery formula in Higgs theory, but similar. So this is a very natural question. That's right. That's right. So yes.
Do you have any clue as to what happens in the general case? Like, do you expect any formula of this sort, or?
I don't have any formula because of this actually. So what we can prove of the 2-1 cable of the figurative knot, what we can prove this is not equivalent to sphere, but the Floer homotopy type of the figurative knot is sphere. I don't know how to write the non-sphere space by using sphere. So I don't know. It seems very hard actually. Yeah. Yeah, that's a really nice question, and yeah, this should be considered in the future. Okay, so I want to focus on this problem, like how the surgeries are related to the real homotopy type. And in order to state the result, let me say one thing. So if two knots are concordant, smoothly concordant, then we can use a TQFT, as I said before. So this gives, so let me say this concordance by S, and then we can get the cobordism map, which is a continuous map from the from the Floer homotopy type of K to K prime, and we have 0 for the action. And if you reverse the orientation, kind of upside down, we have the other way. And one can prove that these maps are 0 for the equilibrium, but if you take a 0 to the fixed point set, fixed point map, then this is 0 for the homotopy equivalent. So this is kind of weaker than the saying that the Floer homotopy types are the same as a space. But like if the k and the k prime are concordant, then like we have this kind of relationship. So when you have such kind of like map in both way, whose 0 to the fixed point map is 0 for the equivalent, homotopy equivalent, let me say this is locally equivalent. So if you have such a map, we say SWR, K and SWR K prime are locally equivalent. So this is really similar to involutive Higata Floer theory. It's kind of space version of local equivalence in the involutive Higata theory. And all concordance invariants I'm saying here are derived from this local equivalence class. Okay, so, and this is a theorem about the surgeries. So let K and K prime, sorry, this is the work of 3 authors. The previous one is also. And K and K prime are the nuts. Whose zero surgeries are diffeomorphic as an oriented manifold. So this, let me say this is orientation preserving diffeom. And then what we can say is Seiberg-Witten Floer homotopy type of K is locally equivalent to Seiberg-Witten Floer homotopy type of K prime. So this means basically the concordance invariants derived from real Seiberg-Witten theory are completely determined by the diffeom class of the zero surgery. It's also super rare, like I haven't seen, like in the Floer theory. For example, the tau invariant or new type invariants, these are like not, known to be not zero surgery invariant. And actually, this is true for Tristram-Levin signature or other algebraic concordance invariant. So if this condition is satisfied, algebraic concordance class is actually the same. So this also shows some, like similarity between the real Seiberg-Witten theory and kind of classical invariants. Okay, so this is the kind of in the 3D, I was comparing the surgery and real Floer homotopy type. But we can say something about 4-dimensional surgery. So let me. Oh, you cannot see, you mean? Okay, sorry. Yeah, thank you for pointing out. Okay, so so let me think about how about 4D. I mean, in a 4-dimensional setting, we have an invariant of 2 naught. So what we can prove is if you have smooth 2 naught inside S4, as I said, there is a degree invariant. But what we can say is this number only depends on the 300 surgery, 5-dimensional 300 surgery along S. So this is kind of similar type of result for the 4-dimensional invariant. So if you have a two-knot inside S4, the normal boundary is always trivial. So you can do the surgery, 5-dimensional surgery, 300 surgery, and to get homology S1 times S4, S3. And the claim is this invariant only depends on the diffeomorphism type of the homology S1 times S3 obtained out of surgery. Okay, so these are the main theorem I wanted to say today. Is there any questions so far? So that means like I have a surgery along this two-knot, and if I have different two-knot, and let me suppose these are diffeomorphic as an orienting manifold, and then we can say that these degree invariants coincide each other. So the claim is this. Actually, this invariant uses kind of information of double branch cover, which I will explain later. But claim is this is determined by surgery.
What's the 5D?
5D. So this is because I'm attaching a 5-dimensional 3 handle. Sorry, I couldn't hear.
Could you just restate in this definition of this analog of local equivalence? I couldn't understand what you're saying with the Z2 Bitcoin, the Z4 homotype equivalence, additional conditions.
Right. So let me have two spaces, which is C over 4Z equivariant space. And if I say these are local equivalent, if there is two maps, which is Z over 4Z equivariant map, and I can think of the Z over 2Z fixed point part, and I'm claiming this is Z over 4Z equivariant homotopy equivalence. So if you have these two maps satisfying this condition, I say X and X prime are locally equivalent.
This implies homological.
Yes. Yeah, local equivalence, the notion of local equivalence is, I think, introduced by Stoffelen, and he introduced this notion in the Floer homotopy type setting first. Okay, so is there any other condition about the main theorems? If no, I will go to the proof. Okay, so then let me go to the proof. Let me first talk about the result on the surgeries. So what we can do for the surgeries is in general following. So let me take the homology S1 plus S2. Let me say this is oriented. And then there is a unique double cover, regular double cover. I mean, the total space is connected. And then I have the involution as a covering involution. And this is a point. Let me take a spin structure on Y tilde, which is does not come from Y. So actually, there are two spin structures you can compute for Y tilde. And I want to fix the spin structure which is not coming from the proof of the spin structure on Y. And then, so let me write this PS as a principal spin bundle. This is a technical lemma of proposition. So if you take a lift of this covering action to the P, now I'm considering this spin structure, which is not coming from Y. So actually, yeah, we can take a lift, but the lift will be not order 2, actually order 4. This is kind of called the odd spin structure. Anyway, so yeah, so we can take some kind of order 4 lift whose square is equal to -1. This is technical lemma, but I will not explain the detail of this, how to prove this, but there is toy model.
You have two spin structures, both on Y and Y tilde. You're saying the two spin structures on Y get to one of the two?
No. I'm saying that there are two spin structures on Y tilde. So this is actually isomorphic to Z over 2Z. And I'm choosing one of them.
Because both, I mean, you have two spin structures also on Y.
That's right.
And you can lift them both.
No. This is going to be the same spin structure on the Y tilde. Okay, so I can think of the Möbius band. Maybe it's line bundle over S1. And if I consider the pi rotation here, -1 multiplication as a tau, and you can, if you take any lift, actually you can prove the square is -1. This is exercise, but this is kind of essential when you prove this proposition. Anyway, we can take an order 4 lift on the spin structure. Okay, so then in the Seiberg-Witten theory, we have pin 2 action, which is U1, JU1 inside pin 2, inside H. And then what we will consider in the real Seiberg-Witten theory is composition of tau tilde with J. It's actually equal to J composed with tau tilde. So this composition has a natural action on the space of connections, spin sheet connection on S and the spinor. We have natural action. Configuration space. And actually this action anti-commute with I. And that's why this is actually it's called real symmetry. And actually this is order 2. And now we have some nice function, which is Chern-Simons-Dirac. And one can see that the Chern-Simons-Dirac is compatible with this I action. It's invariant with respect to I. So I can take I invariant part of the this guy. So this functional. And this can be regarded as, actually I need to think about the gauge group action, but there is gauge group action. And yeah. There is corresponding gauge group. But anyway, what we can prove is if you quotient this space by the gauge transformation, we can trivialize this as an R tilde infinity plus C infinity. So I have some function like on this infinite dimension vector space to R called restricted to Chern-Simons-Dirac function. Anyway, so then just I can take off. So what I have now is CSD invariant part, and I can take finite dimensional approximation of this guy. And then I regard this functional as a Morse function, and I do the like 100 decompositions. It's super big explanation of Floer homotopy type, but I can just take a, yeah, like finite, like Conley index. But Conley index is kind of nothing but 100 decomposition coming from this Morse function. So I can get the space. But it depends on how you choose the finite dimensional approximation, and that's why this lives in the stable homotopy category. So this is, this is an invariant of Y. Let me call this is real Floer homotopy type of Y. Okay. So this is an invariant of three manifold as an oriented preserving diffeomorphism type. Yes. And usually, if you consider the Floer homotopy type for like three manifold with positive edge number, you actually need to think about the parameterized version. I mean, parameterized Floer homotopy type. But actually, in this case, the first bit number we need to think about. So this is kind of real version of first bit number. This is actually the first bit number of Y tilde minus first bit number of Y. It can be also regarded as a dimension of local coefficient cohomology. Anyway, this is actually 0, we can prove. So that means there is no obstruction in this case. The Floer homotopy type is defined as a usual, like it's completely similar way to the original Monolesque construction. So I want to apply this construction to zero surgery to get some relation between the Floer homotopy type of knot with surgeries. Okay, so again, this is technical proportion. So let me write this x0k as zero trace of surgery along k. This is just like I'm attaching the handle like this, and on this side I get zero surgery, and on this side I have just k and S3. And I can take a double branch cover along the 200 core. So let me write this as 200 core. I can take a double branch cover along the 200 core. And then what we can prove is, again, there's kind of unique spin structure on this zero surgery, which have, again order 4 lift. So then we have some real symmetry in the setting of Seiberg-Witten theory for this four manifold with boundary. So yeah, by using like just power filter type things, actually we can provide some cobordism map from this. And this is regarded as a cobordism from double branch cover of K to the double cover of zero surgery. Sorry, might be. Sorry. This is regarded as a cobordism from double branch cover to the double cover of zero surgery. And then, yeah, and we have natural real structure because, as I said, so, and then we can induce the Bauer filter invariant, real Bauer filter invariant. which is going to be Floer homotopy type of K to the Floer homotopy type of zero surgery. But I didn't explain how to define the Floer homotopy type of K, but it's actually same as the three-manifold case. So what I do is take a double branch cover, and there is a unique spin structure. On that guy, the double branch covering action lifts to the order 4 again. And then we can do the completely same story to get some homotopy type. So this is nothing but that Floer homotopy type. And since I have a Seiberg-Witten equation on this four-manifold with boundary, which is like I equivariant, so I can get 0 for the equivariant map. And we can reverse the orientation to get the other way. So this actually shows that these are local equivalent. These are local equivalent. And the important thing done in here is when you think about the cobordism map in any Floer theory, the B plus is very important quantity. If B plus is positive, then like this kind of equivalent theory, the cobordism map will vanish, right? But the point is, in the real Seiberg-Witten theory, the B plus, kind of real B plus, real version of B plus, is B plus of the cover minus B plus of the base, which is actually 0 in this case, even if you choose the other orientation. So this is the point, actually, of this whole story. In the usual Floer theory, the cobordism map simply vanishes, but in the real Seiberg-Witten theory, this is still non-trivial. And it's actually this is, this preserves the all information of local equivalence classes. Okay, as a corollary, what we can prove is, so this complete proof of the surgery is as right. Okay. So as a corollary, we can define the local equivalence class for the three-manifold, and this is local equivalent to the real homotopy type of K. So that means that if their surgeries are diffeomorphic each other, then the Floer homotopy type K and K prime are locally equivalent. This is a proof. And I said some analogous thing in dimension 4, but the dimension 4 discussion in dimension 4 is more easier, kind of more easier than 3-4 case. Let me skip the proof of the second statement. So let me go to the final, this excision theorem. So excision theorem is discovered by Floer, and several other proofs are given by Kronheim and Roger. And we will use the Kronheim and Roger's description of the proving this excision theorem. And in order to describe the excision theorem, so this is kind of excision of the index theorem type things. So I will take double cover. So this is a neighborhood of K, removing it from S3. Sorry, can you see? This line is fine. Yeah, maybe I can. Oh, excision theorem is implies satellite formula. Excision theorem is stronger than. I didn't say. Sorry, sir, I didn't say. Yeah, you can imagine after writing everything, I think, yeah. So this is Y1 and Y2. Yeah, this is kind of same as the construction of excision cobordism, which is done in many Floer theory, other Floer theory. But with 0 but to the action, we are thinking. So I'm taking the double cover along the, sorry, regular double cover of the complement of the knot, we have double branch, and I'm thinking the double branch covering space of S1 times D2 along P, the satellite plan P. There is an involution tau 2. And instead, here I want to think about the unknot. And the final one is kind of trivial. Sorry, torus with the trivial core. I have a branch cover along that, and I have involution. So I will kind of do the switching, making manifold by switching these guys. So, but the key input is this form, the manifold with corner, this guy, times T2. Okay. Yeah, this is really same as like known excision cobordism construction. But I'm taking double branch cover. So, and then let me write Y as the union of T1, T2, and so that I can get just double branch cover of PK. So if you, suitably glue the manifold, then you can get these four manifolds, three manifolds. Okay. And I will construct a cobordism between them, four-dimensional cobordism between them. Okay. In the following way. So I have this manifold with corner, this T, this times T2. And here I put the Y1 prime times I. The boundary is regarded as the torus times I, so I can glue this along here. And the minus, we need to be a little bit careful about the orientation, but suitably put in this way. And then by construction, you can see the corresponding three manifold here is this guy and this guy and this guy and this. And I have a natural action involution on this T, which is, so this is because, sorry, this is weird. This is just T2, so just pi rotation on the first coordinate. And we can glue the equivariantly. We have the double covering action in these guys. We can glue this group action as well. So this gives, so this four manifold W has an glued involution. Okay, and that's all. That's almost all of the proof. So I have a cobordism from. So this can be regarded as a cobordism from the double branch cover of K union double branch cover of the P of the unknot to the S3, which is double branch cover of the unknot union double branch cover of the K. And relation to like usual excision cobordism is if you divide this four manifold by group action tau, then you can get the original excision cobordism. if you think about this kind of cobordism map in the original theory, if you divide it by the tau action, then V plus of the downstairs manifold is actually positive. So that means if you think about some equivariant Floer theory, the cobordism map just vanishes. But here is also the strong point of the real cyberweighting theory. So real cyberweighting theory only refers like real V plus is it's kind of V plus of this guy minus V plus of the constant manifold, which is actually 0. So that means this is kind of negative definite cobordism in real cyberweighting theory. And then, yeah, just the remaining part is kind of routine. We can get, we will get the kind of unique spin structure with order 4 lift. And then we can associate the Bauer-Fruta invariant for this guy. From this guy to this guy, and the other way is, again, even if you reverse orientation, this, you can find this. You can have this. And these are the homotopy inverse each other. And the proof of this existence of homotopy inverse, this is almost same as the original action theorem. If you you put something like this, compose, and then you will do some surgery, parameterized surgery, to get the product cobordism. And product cobordism is identity in the real cyberweighting theory, so that's completely the same as the original story.
Are you using something
Mm-hmm.
T3
Right, T3, real cyberweighting homotopy type of the T3 with certain involution is S0. Yes. Okay. Oh.
It's more that you're using. I mean, are you really using the real B plus is 0 here? That might be quite productive. But there is a good equivalence. But you're using. You want to prove excision. Do you really? Does that go directly into the proof that real B plus?
Sorry. This was kind of misreading. Yes. But if B plus is 0, then it's not isomorphism anymore. But so that's why I said it. So in the other Floer theory, this cobordism map will vanish. I wanted to emphasize this, but in the proof, we don't use. Yeah, this is all I wanted to say today. Thank you for listening.
Did you use some similar kind of construction for more general statement that you have 2-3 manifolds with T2 boundary and you prove them in the real cyberweighting?
Yes, we can prove. Yeah, we have written such a general statement in the paper. Yeah, but what we need to assume is the involution on the torus is kind of fixed one, like this torus action, and we need some compatibility of the real spin structures.
What would be the generalization of winding number condition?
No, it's still no. Winding number, we cannot improve the winding number condition actually.
No, I know, but like when for your satellite one, you had this constraint on the winding number. So for this more general statement, what would be the analog of that condition?
Isn't it what makes the involution act as you want on the ingressivity of the torus?
I think so. Yeah. That's right. Yeah. Kind of the compatibility of the over action.
So right here you're using that you have when you do this cobordism condition, you have this involution on the boundary of your satellite.
Yeah. Right, right.
Do you expect that you can make kind of similar statements for other types of surgery operations, provided you could set up the right orderism between, medical associates to cover certain, like sort of the top level inputs? Do you expect any of this to work in different types of surgery?
Sorry, you said the connected sum type operation? Yes.
No, for like, so if you, the sort of, some of the top level inputs that you're talking about in terms of like movement proportion,
Uh-huh.
like branch covers of
Uh-huh.
original thing or branch covers of surgery,
Uh-huh.
et cetera. Like, do you think that if you had those types of top level inputs, but for different types of surgery, not necessarily surgery on a knot in the 3D case or a two knot in the 4D case,
Uh-huh.
on like let's say the torus
Uh-huh.
or these other things, do you expect that you could get
Other surgeries like
surgery?
thorax surgeries or such kind of things. Yeah, like yeah, maybe depending on the situation, but the here why we are using so T2 is very important in this story, right? So because the important thing here is so there is nice involution here, and so in the real cyber-Witten theory, so this manifold looks like S2. This is the point actually, and for S2 we have a pi rotation, and this also looks like S2. But for higher genus of surface, there is no corresponding nice involution. So that's one reason we are just using the surgery on T2 or S2 or T2. But maybe for torus type surgery, if your involution grows nicely, I expect that, there should be some kind of nice formula. Yes. But for higher genus, we have no candidate of nice involution on this manifold so that we can see this as a sphere in the cyber-Witten theory. Yeah, that's one aspect, but yeah.
Can you say a couple of words about how you prove the
Okay. Sorry. Just decompose the double branch cover. So the degree invariant is defined by considering the order 4 lift of the spin structure and take a real structure and forgetting 0 the action, considering a degree of real powerful invariant. That's the definition. So we will decompose it into, S4 is just S4 minus the neighborhood of S union S2 times D2. So decompose again the double branch cover into 2 parts. And for the surgery, we have similar things, right? So surgery, the surgery is S4 minus the neighborhood of this guy, union D3, it's not true. S2 times, D3 times D2, so, D3 times S1, right? So this is the meaning of surgery in 5-dimensional setting. So we can take double cover on this form manifold as well. Regular double cover. So this is again regular cover of the complement with T3 times S1 cover. But so the boundary is T3. S1 times T2, S1 times S2. And we have some kind of concrete involution on this guy. And one can prove the real Floer homotopy type of S1 times S2 is equal to S0. So this is kind of same as S3 inside real cyber-Witten theory. Okay, you could understand? by the way, this invariant of homology is 1 to 3. So there are several other gauge-theoretic invariant called Furuta-Ota invariant and Moroka-Rubin-Sobolev invariant, using the counting of like the instant on Seiberg-Witten equations. And this real Seiberg-Witten theory also gives some invariant of homology is 1 times S3, but we can easily prove these invariants are totally independent. Yeah.
You stated this question about surgery, general integral surgery. What would be, I mean, it looks like the same kind of techniques can, at least for some of the surgery, even.
That's right, that's right. So we are expecting the 4N surgery works. 4N surgery works. 4N surgery, yeah. So yeah, 4N surgery have the same information as a zero surgery and real surgery, like free homotopy type.
What is real Seiberg-Witten here? S1 times sigma?
So for the real Seiberg-Witten theory, we need some nice local coefficient to take a double cover, and I need to take a spin structure on the double cover. So so the real Seiberg-Witten theory can be defined like yeah, we need some condition, but at least double cover is needed. So and that's why 2N is imposed. 2N is imposed, but for some issue of the spin structure, in order to apply the same kind of method, we need to 4N. Yeah.